So picking up with and finishing on plan comparisons, the issues in using with plan comparisons. We want to use plans comparisons when there is a meaningful subset of comparisons, i.e. the number of comparisons is less than the degrees of freedom between. So remember that in that case, degrees of freedom between, if you only have three conditions, is 3 minus 1 is 2. So the only reason we would ever use planned comparisons if we only have three conditions or three groups in an ANOVA is if we're only interested in a single comparison. Now, as you increase the number of conditions, the number of planned comparisons you can use also goes up. So for example, if we had 5 conditions, 5 minus 1 would be 4. At that point, as long as we're running less than 4 paired comparisons, the planned comparisons, if those were driven by hypotheses and theory, and we knew we were going to do more than just degrees or less than the degrees of freedom, that's when we'd move forward. So again, if we had 5 conditions, 5 minus 1 is 4, degrees of freedom between is a 4. As long as we're running 3 or less planned comparisons, that would make sense. In other words, if you're running the number of planned comparisons equal to degrees of freedom, you're not gaining anything from it. In other words, the Bonferroni adjustments that you'd have to make start to actually make this technique less successful at finding differences than just looking for all differences. But if you're actually looking for the number of differences that you care about is less than the degrees of freedom between in the number of comparisons you're going to make, that's when actually doing planned comparisons or a priori comparisons makes sense. So you can determine that subset a priori. Again, this should not be driven by data. You should not be deciding to do an a priori planned comparison when it wasn't planned and it wasn't a priori. And again, as long as you're following these guidelines, it tends to be more statistically powerful. You're more likely to find the differences if they're there. And honestly, it is a little easier to abuse. You're kind of getting to ignore things that you want to ignore. That's why it has to be done ahead of time. It has to be planned. Because if it isn't planned and you're driving it by data, well, I'm going to ignore these two comparisons because it's clear that they're not statistically significant, but you were expecting them to be. You're now choosing a statistical technique that is much more likely to find differences by ignoring differences that aren't there that you thought were going to be there. So there's no thought police that can come and make sure you're not doing this, but to be true to yourself and to be ethically true to the science of psychology, only do these if it's pre-planned, based on theory, you've already determined it before you ever look at the data, and the number of comparisons you're making is less than the degrees of freedom between. The final thing I want to talk about is trend analysis, and this isn't done as often as it used to be, but it's still a technique that may occasionally come to your aid. Trend analyses are computing, again, using contrast, but we're actually going to use a little equation to change the top of the equation of our F to ask the question, is there a linear or quadratic trend in our data? The number of trends we can look at are limited to a minus 1, which is basically number of conditions again. So for example, in this case, we could look at both a linear or a quadratic term. Now the first thing that we need to do is to create a contrast. We need to choose some numbers. And these numbers can be pretty abstract, but generally speaking, there's a couple of rules. They have to add up to 0, and the smaller the numbers, the rounder the numbers, the better. So for example, if I was wanting to look at a linear trend and ask, above and beyond the differences between the means, do I find that the criminal group is the lowest, the non-criminal group is in the medium, and the unknown group is at the highest, then I would actually add the contrast, -1, 0, and 1. So notice how I'm using -1, 0, and 1 to create a linear trend. Low, medium, high. Notice that -1 plus 0 plus 1 equals 0. So the first thing we do when we do a trend analysis is we grab arbitrary numbers to create a trend. Now the quadratic equation would be a bend in the data. And in this case, I've got 1, -2, 1. So high, low, high. Does that explain my data better than just the group differences? So this is kind of asking the question, beyond the categorical nature of my IV, is there also a linear trend that I'm expecting, and does it explain some of the difference in my group in a meaningful way? So this is kind of bringing ANOVA a little bit back to multiple regression. So again, the numbers are arbitrary. You could easily go with negative 100, 0, positive 100, as long as they add up to 0. You could go 50 minus 100, 50. Again, they would add up to 0. It's just simpler for the math and easier to keep track because they are arbitrary, to keep them as close to 0 as possible while maintaining that 0 when you add them together. Okay, so once you determine whether you want to look for a trend that is linear or quadratic, and again, if we actually had a 4 conditions, 4 minus 1 is 3, we could also look for a quintetic relationship. So we could actually look for 2 bins in the data. So that's that A minus 1. That's simply telling us how many trends could we legitimately look at. We're going to just look at the linear trend, though, as far as calculation. So the equation for the linear trend requires us to take that coefficient, that contrast that we chose, negative 1, 0, positive 1, and the original group means. And what we're going to do is, first, there's the collapsed equation to your left, but the actual equation that we're interested in is shown to your right. What we're going to be doing is taking the small n. So again, this works best with conditions that have the same number of people in them. In this case, again, criminal, non-criminal, and unknown had 5 people each, so the first number is a 5. And again, I'm at the right equation where it says m squared and mean squared, and I'm looking at the top of the equation. I am then going to multiply each mean by its contrast. So 8 multiplied by negative 1, 0 multiplied by 4, and 1 multiplied by 5. So that's going to give me a negative 8, a 0, and a 5. I'm going to add those up, I'm going to square them, and I'm going to multiply them by 5. So that's what's happening on the top of the equation, and you can follow along with that as the equation goes forward. So again, negative 8 plus 0 plus 5 becomes negative 3. Negative 3 squared is 9. 9 times 5 is 45. The bottom of the equation is simply taking the squares of my contrasts. Negative 1, again, that arbitrary number, multiplied by itself is 1. 0 multiplied by itself is 0. 1 multiplied by itself is 1. We're going to add those together. 1 plus 0 plus 1 is 2. So now we're simply going to take a look, and we have 5.9 divided by 2. That becomes 2.25, and at the very end of the equation is everything gets divided by 2. And in this case, and that 2, by the way, is k minus 1. It is your degrees of freedom between. So 22.5 divided by 2 is 11.25. So we have just created a new mean of squares representing the top of the equation, and it's representing actually whether or not we actually have an effect size at the top of the equation that is above and beyond the difference of the mean. It's actually a linear trend. So what we're looking for here is that the criminal group is the smallest, the non-criminal group is the medium, and the unknown group is the highest. That's what we actually set up with those contrasts. Now, of course, in this case, we simply go back to that initial F ratio, and all we do is replace the original mean squares, the mean difference, with now the trend analysis. In this case, 11.25 is divided by that mean of squares within, and again, we hand calculated this 2 audio lectures ago, 5.33. We get a 2.11. And then to determine the significance is done the same way with any standard ANOVA. We're going to look at our degrees of freedom. K minus 1 is 2. And again, our degrees of freedom within, n minus k is 12. And we're going to look at that table to see, is a 2.11 significant? And indeed, it is not. There is not a linear trend to the differences between our groups. Like I said, this is not a common technique that is used often because generally speaking, we treat categorical variables exactly as that, categorical. However, there are some applied settings where you may have an additional hypothesis of a directional change. So for example, you may have no treatment, 1 hour of treatment, 2 hours of treatment, 4 hours of treatment. Not only are you interested in the differences between the treatments, you also want to ask, do I see a systematic pattern of increases above and beyond the mean? That's when a trend analysis would actually be useful. So summary, across all of this information, Tukey's HSSD on a significant difference, we're going to use when we don't have a hypothesis about the nature of the effect, we don't have a priori planned comparisons, or when all the comparisons are important. And again, if the Tukey's HSD does not find differences when the F said we should, we're going to look at potential other types of tests. Or if we're very concerned about accidentally claiming an effect is there when it isn't, we might move up to a more rigorous test. And again, we're going to use the a priori test, a series of paired t-tests adjusted for alpha by a Bonferroni's correction or another correction technique. We're going to use when we can identify a few important comparisons in advance. So hopefully this covers everything you want. And again, if we're using an a priori test, it can be argued that we do not need to do a Bonferroni correction. However, that is going to vary from person to person. Generally speaking, I'm a big believer in always doing the Bonferroni correction. When would we actually argue not to? Well, when we did an a priori series of tests, we had a significant F test, and none of our a priori tests found a difference. In that case, we would make the argument that the Bonferroni test was too rigorous, and therefore we would rerun those a priori tests without that Bonferroni correction. Again, we're going to try to be as rigorous as possible when we have a significant F. But once we have that significant F, it gives us a little bit of license to try to do what's right the first time, but also those differences are there. We have an overall significant test. So let's find them.